Hi everyone, this is Group 72, Crocodilo, and today we're going to talk about our self-designed AI agents to try to win the sequence game. The group dived into the game and developed 6 different agents as listed here. This presentation will mainly focus on Q-learning and how and why we switch from Q-learning to deep Q-learning. In this section, I will walk you through our transition from classical Q-learning to a deep Q-learning. Recall that the sequence game is partially observable, stochastic board game, and we first frame it as a Markov decision process in order to apply Q-learning. However, we encounter several serious limitations with a tabular Q-learning approach. The first one is that the Q-learning table is really large, since sequence game has a large state action space. Then the Q-learning is not that generalizable and time-consuming. This is because in a game as large as sequence, it is hard for the agent to see all configurations. Hence, a QW approach cannot generalize, and the model would take an impractical amount of time and computing resources to converge to anything close to optimal. Hence, deep Q-learning approach is implemented. By introducing a neural network, we can generalize across unseen board configurations and avoid storing every state action pair by only saving the network weights. Then let's have a look at the network we're going to use here. The first one is the CNN. The team flattened the 10 times time board into a tensor of shape 4, 10, 10. Each of the 4 channels represents one of the 4 values at each cell as listed here. We then feed the tensor into a small CNN network, so the net can see spatial patterns directly like chains of connected chips or blocking threads. Then eventually we flatten to an 8-dimensional board feature. That's all. The second one is the FMN. Each action is described by play card, draft card, type, and coordinates. We only have one hot encoded draft card and type. This yields a 55-dimensional one-hot vector. This FNN would provide a 32 dimensions action feature vector. Then we take the 8-dimension board feature from the CNN and the 32-dimension action feature from the FNN, combine them into a 40-dimension vector. This will be passed through a final linear layer of size 40 and to produce a single scalar Q value given state, action, and weight. And I will pass it to Tony now.
Instead of updating a Q table, like in traditional Q-learning, we update the neural network's parameters so that it predicts better to match the target Q values. Here, Q as a theta represents the predicted Q value for a given state action pair using the current network. The loss is computed as the difference between its predicted Q value and the target Q value, which is also known as a temporal difference error. This loss is then minimized using the backpropagation, allowing the network to gradually adjust its parameters and improve future predictions. In our design of online learning, there will be no look-ahead updates because the reward of next state is not known. As a result, we must wait for the game to progress to the next state before we can update our network. As shown in the diagram, we need to move forward to the next state in order to observe the reward and update the neural network's parameter associated with the current state.
Hi, I'm Jackie. I'll take over for the reward shaping part of our DeepQ learning agent. Reward shaping provides an intermediate feedback that guides a DeepQ learning agent toward a desired behavior, improving the convergence and speeding up the learning. In our design of the rewards, we focus on giving positive rewards such as the following. Completing one sequence yields a reward of 500. A problem we found when training the agent with reward function is that agents started to behave illogically. One example is agents started to try to block non-existing opponent sequences. We realized this issue actually stemmed from how the rewards are assigned during training. More specifically, in the initial design, whenever the opponent made a sequence, we'll deduct a very large number from the reward, and no matter what the agent did in the subsequent moves, they will always have a negative reward. The misleading reward signal meant that the agent failed to learn the correct association and led to undesirable behavior, and we fixed our reward shaping after that and reduced our penalization. Another characteristic of our DeepQ learning agent is batching. Our original implementation is based on Q learning and used one training sample per update, which is really slow and unstable. What we did was we introduced a global replay buffer to store all encountered experiences, and this improvement enabled batch training with 1024 samples per update. And as a result, the training became 1000 times faster compared to the previous approach. However, with this new approach, we have to wait before the buffer's full to start training. However, we consider this as a really great trade-off for the speed it gave us.
Although neural networks are powerful tools for learning complex patterns, but they come with significant limitations. One of the main issues is its interpretability. It is very difficult to understand why the agent behaves incorrectly or trace its decision-making process. While batching makes training computationally efficient, achieving good performance will still require a long training period. Another limitation is that the agent needs many opponents to play with and learn with. Make sure it does not overfit on a specific opponent. Finally, the training loss is often unstable and doesn't reflect on real improvements. So we must rely on win rate to evaluate the training progress. One key improvement is to use a training network plus a target network. Our current DQN uses the same network for both prediction and target calculations, which leads to instability. Instead, we introduce a second, frozen copy of the main network that updates less frequently. This can stabilize the training by decoupling prediction from target calculation. Then the updating rule introduced before changes to this, where the Qs-A-theta- is the target network.
Hi, I'll begin with our demo session. As we can see, currently our agent is a blue and we are 2 steps away from winning. We only need to place a chip in a K heart and a 10 heart. We already have the K heart in our hand, and let's see what our agent will do. So our agent will first, it will play the K and then draw the heart from the draft pile, and play it on the board. And we want to specify that this is actually pure learning from our agent, and we did not program this by hard code or anything, and we're really impressed by the agent.